afternoon, everyone. And this is our topic, post-retrieval algorithm for interferometric frequency resolve optical gating based on differential evolution. And I am speaker Xiantang. This is our outline. And first, this is the abstract. And the main idea of this paper is to introduce an algorithm named differential evolution into the iFrog. So there are two main characters in this paper is differential evolution and the iFrog. And there are some advantages, and the experiments and numerical tests are shown in this paper. So the introduction, and first I want to talk about the iFrog. What is the difference between frog and iFrog? I think frog is so familiar with you, so I won't explain. And what is the iFrog? The difference between them is iFrog uses two beams with collinear. And what is the advantage? The first advantage is if they are collinear, it can apply to tight focusing. Why frog cannot use tight focusing? Since if the two beams are not collinear and you want to use the tight focusing, you will find difficulty in overlapping the two tiny spots on the BBO. So but if the beam is collinear, there's no difficulty. And there's still another advantage. Since they are collinear, the detector will receive all the information, more information than the frog, since the frog only detects the cross-turn without the individual beam. And there are some problems of the algorithm with iFrog. Since, for example, they may not use completely all the information of iFrog, or it takes a lot of time in computation since the data is too huge. And also, and so this paper will introduce the differential evolution, and the differential evolution can solve all the problems I said. And there is some advantage, such as all available information of an iFrog can be exploited, and the accuracy and noise resilience of the new algorithm outperform GP, generalized projection. So after introduction, let's jump into some detail, post-retrieval. The first equation is the iFrog trace. It's simple. And it contains three subtraces, equation 2 to 4. And each subtrace has its own function. And let's take a look at it. The first one is B0. And it is DC band and contains SHG frog trace so that it can be used to retrieve pulse shape but cannot retrieve the chirp pulse very well. And the second one is B1, FM band, more sensitive for the phase of the pulse, so it can be advantageous in the retrieval of the pulse. You may wonder that it looks like FM band is completely better than DC band. So why we need FM band? But wait a minute. Since FM band have more much data information, so it takes a lot of time to calculate the FM band. So we need DC band to narrow down the computation. And the third one, B2, is SHM band. This one is independent from the above two. It corrects the error due to a jitter in the delay measurement. This figure is the flowchart of the DE algorithm. What is differential evolution? It's a kind of genetic method. What is genetic method? I will say later. And after we have an ifrag trace, we want to retrieve the pulse. At first, it have a lot of initial random guess, and we can calculate the error. And we randomly select 3 electric field vector from the initial guess. And the one with minimum error is EA. And after we do the mutation, we have a new electric field vector. Notice that I used to say the genetic method. What does that mean? Genetic method means we want to preserve the good gene while kick out the bad one. So after we produce an offspring, we can do comparison between the new one and the old one and kick out the bad electric field vector. Okay, and when we keep doing this cycle, we can finally converge the pulse retrieval. So there are some key points. Seeded with a large number of initial random guess rather than a single one can reduce the risk of local stagnation. And with DC and FM band information, the algorithm can be seeded less number of initial random guess to speed up the program. Not surprisingly. Okay? Numerical test. Okay, the first two retrieval, these two from the 10% noise level ifrag trace, and it used FM band and DC band to retrieve the pulse. You can see that FM band is better than the DC band. Yes, and the lower two figure also shows that the FM band show more detail than the DC band. And while FM band is better, we still use DC band in combination with FM band to reach a redundancy of data set. Okay. The above two figure is the pulse retrieved from a GP-based frag trace without noise, and with 10% noise. And you can see it's roughly the same. So DE ifrag has a good noise resilience. And if you want to use the GP frag and reduce the noise, you will have a side effect that the side lobe, satellite pulse is underestimated. Yes. Okay, the marginal correction. There are some reason will cause the error, such as spectral response of spectrograph and quantum efficiency of a charge coupled device and distortion of the spectrum. And how to correct this? You can do these two calculations. Calculate from flux trace and direct measure power spectrum. These two should be the same. So you can do the comparison, and it should be self-consistency check.
And I'm talking about the timing jitter correction. It's caused from the few reasons, just like mechanical vibration or the fluctuation of the air density or the non-uniform movement of the delay stage, which distort each delay step. The correction procedure can be realized by measuring the phase of modulation equals to 2 omega 0 plus delta omega multiplied tau of the SHM band. And we can quickly removing the modulation by the B2 multiplies cosine phi multiplies the B1 multiplies the cosine 1/2 phi. And we can see the figure 6 over here. And impressively, the pulse is perfectly reconstructed after the timing jitter correction. And there is our experimental measurement setup. It's a current length Moloch disulfide laser generate the pulse which centers at 800 nanometer. Pulse duration is only about 10 femtosecond, and with the pulse energy of 7 nanojoule. Separate measurements were also made using the commercial fuel cycle spider. And the additional dispersion is taken into account in all the results by subtracting this additional dispersion due to air from the spectral phase retrieved by spider. And I'm talking about the transfer limit pulse. The figure 8 is the IFROC measurement for Fourier transform limit pulse. A is the measured IFROC trace in linear scale, and the B is the Fourier transform of the trace along to the delay axis. And we can tell that the SHM band is approximation to a straight line, which means the delay stage movement is sufficiently accurate, and the timing jitter correction procedure can further improve the measurement data. And the finer detail of the measurement data are only found on either positive or negative delay. But ideal IFROC trace can solve this problem because it is symmetric by the delay. The detail found the only single side of the measurement substrate is further only can solve this problem. And furthermore, as the algorithm produce and feature on the both sides of the Furthermore, as the algorithm produces the feature on both sides of the substrate, any produced value between these two measurement value, it will get the same error for the measurement point. And we can see from the G and H, the 7.6 femtosecond pulse retrieved by DE frog is in an excellent agreement with the spider measurement. And furthermore, in frequency domain, DE frog retrieved both the phase and the spectral intensity. And I'm now talking about the chirp pulse. We can note from the figure 9 that figure 9 is the IFROG measurement for chirp pulses. A to C is the measurement IFROG trace, and D to F is the Fourier filtered DC traces of the A to C. We can see the figure I that the commercial spider is no longer to work for the longer pulses, that if the pulse is longer than the 60 femtosecond, it will fail. While the increasing pulse duration should not be the problem for the DE frog. And along with the added dispersion measurement by DE frog, we can see the figure 8H. The latter value were obtained by subtracting the measurement spectral phase of the Fourier transform limit pulse from the chirp pulse measurement. And C is the low signal to noise ratio. In figure 10, we identical the DE frog is much less effective by noise, the comparison to generate projection retrievals. In time domain, we can see the C to F. The numerical simulation, DE frog retrieve very similar pulse for both trace, but GP on the contraction suffers from the higher uncertainty in retrieve time domain pulse envelopes. And the difference in the retrieval field to the two algorithms are most pronounced in the frequency domain. We can see by G to J. In the figure I and J, the large standard deviation, especially for the intensity, was enhanced. It caused the large error of GP to get the stock of the local minimum. In the conclusion, the first DE frog is based on the genetic algorithm differential evolution and can use all the other substrates contained in an IFROG measurement simultaneously. Second, the DE frog can also solve the incompletely data set or the several impression measurement like additive noise, imperfect spectrum response, and the time jitter, which can compare with the GP, spider, and SHG frogs. And even with the higher attenuation, IFROG signal before detection were made to further gauge the noise resilience of DE frog. And the fourth is the collinear beam Geometry allow tight focusing and avoid the geometry beam smearing. And this is our reference.